Okay, hello everyone. I'm Munira, PhD student from Mechanical and Engineering Department. So today for this project, I'm going to present on ontology development for the additive manufacturing in dental applications. So basically, the applications of using, so the usage of the additive manufacturing technologies in the dental applications. So maybe some of you might not know what is additive manufacturing all about. So basically, it is also called as the 3D printing process, where basically the concept of the operations for this 3D printing is they build the objects by putting layer by layer, instead of, that's why they call it as the additive manufacturing. So, so they use that, it is under computer control. So of course they are using the CAD/CAM systems as part of the processes. And then basically, actually for the CAD/CAM system, it has been used in the dental applications before, but another processes that use the CAD/CAM system is a subtractive process, such as the CNC milling or CNC machining process, where it becomes wasteful because they need to have a block of materials, solid of materials, the block of material, and they remove the material from there. So it becomes wasteful, and it's also lack of complexity, whereby for this additive manufacturing process, it can have any shape. So currently, these are the applications, some of the applications of the 3D printers that have been used in the dental applications, which is the crown and bridge, braces, and also other medical appliances. So from using this, they have these various processing steps where of course they need to use the data acquisition, where they need to have a scanning process, and from that scanning process they will obtain the data, where those data will be manipulated and processed for using the CAD software, and then from the processed data by the CAD software, they will use it to manufacturing the structures in the desired material. So basically, because this is the applications of the specific applications of the additive manufacturing process, so my ontology that I'm developing is focusing more on the processes that will require us to have the material to produce the product and require certain data information entity to support the process. So, as we talk about the manufacturing process for this application, so it closely related to the product life cycle, where it will involve designing, okay, and then construction, the usage, construction and the usage, and then recycling, where the usage of this is the information link between the phases. So I start my ontology by identifying what are the processes involved in the product life cycle aspects, where basically I'm not covering on part where the patient comes to see the dentist and so on. I'm just covering on how they use the additive manufacturing process in these dental applications. So first, it started with the acquisition of the 3D patient model, which is the tooth model or jaw model. Okay, so this model could be in the physical model, maybe they use the clay, or they use a digital model from the scanner. So from this model, they will create the STL file, which is the stereolithography file. That is the language that the machine able to understand to do the process. Okay, so all of these are done or designed in the CAD software. So once they have the design file, they will prepare the model for printing, where here they need to specify or they need to structure the file or to structure the model in terms of the layers. How many layers? Because we are talking about building the material 3D object layer by layers. Okay, and then once they have the model with the layer structure, they will start doing the 3D printing process, where those data will be sent to the printer and the material will be laid down layer by layer. And finally, once they have finished the process of the 3D printing, that sometimes they need to have several post-processing activities for the finishing parts of the product. Okay, so here sometimes they need to remove the support, sandblasting, and so on, all of those processes involved. So, in building this ontology, so basically I'm using the top level BFO, where we have the continuant and occurrent, where the focus more is on we start with the planned process first. And then, of course, with the planned process, we need to have the material entities and also the information entities. So, this is the link that Barry gave to me for a reference, where we talk about the product life cycle, which is part of the planned process, and it is part of the FO. So you can see here, this is the sequence of the process, where all of this process actually is part of the product life cycle. And of course, it is also a planned process. So this process precedes another process. So after this process will follow, and so on. So I will cover on each process one by one. So we start with the 3D teeth model acquisition, where from this model acquisition, we will have the output, which is the 3D tooth model of the patient. And then from this 3D tooth model, it will become the input to the design process, where in doing the design process, they need to have the product requirements as well. So these product requirements, such as the shape, the size, the basically what the product should look like, what the product that needs to be produced. So this product requirement will guide the design process, which finally will have the output, which is the STL file for the machines later. So as I sort it out in terms of the process, information entity, and material entity, so once you have the input, guide by this product requirement, and you have the output. So you can see here, it moves along the time. So and then for the production plan, next process after the design process, they will move to the production plan generation process, where the STL file that becomes that is the output of the design process will become the input. And this production plan generation process will need these design parameters to assist the process. So the design process, the design parameters could be like the So the design parameter could be in terms of the angle of the product, the gap, and also other types of parameters for the process plan, for the production plan to be generated. So as I put it back into the flow, okay, so you can see here the flow. Here we pick up your input of this, and then guided by these design parameters, and produce the output of the production plan. And after the production plan, they will move to the 3D printing process, where this production plan will guide the 3D printing process. And of course, the material here will become the input to the process. And in order for the process to do the work or the operations, they need to have the process parameters to be used inside here. Actually, before this, I used the word control, because they want to use the machine, they need to put the parameters for the machines to run, such as the speed, the layer, thickness, and so on. And then it will produce the output, which becomes the semi-finished product. This is the ideal situations. But sometimes it will have some defects or reject or something to do like that, so it will become the portion of waste. Okay, so as can be seen here, So this is our material entity. So I put it in terms of the material portion of materials. And then this is a semi-finished product, which is coming from the 3D printing process. I cannot call it as the finished product yet because it needs to go through the post-processing process. So next, for the post-processing process, still they use the production plan that has been generated before during the production plan generation that guides the process. And this semi-finished product becomes the input, where the output will be the finished product, and some of it, if it has some problem, it will become the portion of waste. So it's a bit messy, that's why I put it in the separate processes. So you can see the flow. Now we have the finished product as one of our material entities. So once we have the finished product, they need to go through the quality inspection process, where in this quality inspection process, they will refer back to the product requirements that will guide the quality inspection process, where the finished product will become the input. And finally, those final product, if it satisfies the quality of the aspect that we need, so it will become a final product, or else it will become the portion of waste. So finally, for the portion of waste, we need to have some process to end the operation. So it could be, we can do the recycling or reuse or disposal. So that is the end of life process. So basically, these are how I saw it in terms of inside the protege of the owl. Okay, so we have the plan process here, which is where the product life cycle is the subclasses of the plan process, and we have all of these processes where I give the relationship where this have to precede this design, and then proceed to the another design, another process. And for the material, so I classify in terms of the few areas, so which is for the portion of material separated from the processed product, that we have a final product, finished product, and semi-finished product, machine use, tools, and also the portion of waste. And this is for the information content entity, where we need to have the 3D tooth model and STL file as a data item, and then the directive information entity to guide the processes, where we have the product requirements as a guide to the design process, design parameter as a guide to the production plan, plan specification as a guide to the 3D printing, and process parameter as to control the to help the 3D printing to do the work. So as a conclusion, I think that this is a very good tool for those who are going to do the process planning. Okay, and also if someone wants to do the design in the manufacturing industry. Okay, but of course, I don't have much problems on the processes, but because we are talking about the application of these processes in certain area, so you need to have more detailed data and parameter in the information entity. So I'm looking forward to expand the ontology as well.
One quick thing, I think you have a typo on slide 11. I think you have a 3D tooth model where you should have STL file, right? Is that right?
Oh yeah.
Just small thing. But what's the difference between guides and used in?
Guides is something like you are referring to it, but in the 3D printing, you need to use that process parameter in order for it to move or to process, to do the process.
Okay, because most of the parameters, like requirements, kinds of things, were guiding. But one time there was a parameters that was used in, but
yes,
not guided. What?
Because let's say for this product requirement, you don't have to set it, but you need to refer it. For example, the engineering drawing or the technical drawing, something like that. But for the process parameters, so for example, you want to run the machine, you have to specify what would be the speed of operations, what would be the thickness of the delay thickness of the operations, and so on.
Okay, that's helpful.
I saw several on your slides, and also on this one, the has input direction of the arrow is wrong. That's systematically. There were a couple of things where I saw that the all-sum principle was violated. But the most important one, when I got it, am I right that what you call a finished product is at the end of the post-processing?
Yes.
And then the final product is after quality inspection.
Yeah.
Now, okay, this is the problem. So you get your finished product, and you look at it, and you say, that's a good one, okay? So do you agree with me that by just looking at it, nothing changed in that product?
Can you repeat the question?
All right, so I have this cup, so suppose this is the finished product. And I look at it and I said, all right, that's good. So now it becomes a final product, right?
No, because for us to say that it is a final product, there are certain qualities that have to be fulfilled. There are certain tools that need to be used.
Yeah, exactly, that's what I'm saying. So I do all that, and then I say this satisfies all the criteria.
Oh, okay.
All the criteria, so is it. So nothing actually changed, right? So, but nevertheless, according to your ontology, it would become suddenly be an instance of a different class.
Oh yes, I haven't think about that.
Yeah, so I think you are there confusing terminology with ontology.
Or roles with the things that have the role.
Maybe.
That this is an issue. I don't think there's an easy solution. Yep.
So can you go to the second to last slide? It's 22. Yeah. So I wonder how I feel like you're going to run into these problems where you use a term like angle, and use it to mean something very specific, when other people use it to mean something general. So how do you make your terms more specific so that angle doesn't get confused with the general term of angle, even if you mean it in a specific context?
Actually, I should include the pictures of the cap that have the label with the angle and so on. There is a terminology that you use there.
But I think when people in general use the term angle, they don't mean a cap design parameter.
Yeah, I agree that. Thank you.
So one solution would be to change the name to cap design parameter angle. Another solution would be to point out that each of these terms in the fully developed ontology will have an ID, which will be a number. And then the number for angle here will be quite different from the number for angle in a generic geometry.
But isn't it the same kind of angle? They refer to two different...
Unless you're trying to put those two ontologies together, it needn't matter.
Okay.
Of course, in the end, we do want to put all the ontologies together.